Okay, let's take a look at rational expressions. And as we mentioned in the last video, rational expression is simply the quotient of two polynomials where the denominator does not equal 0. So for example, if we take x squared plus 3x plus 2 over x squared plus 4x plus 4, then we have a polynomial in the numerator and a polynomial in the denominator. And this is our rational expression. So we have our x squared plus 3x plus 2 being divided by our x squared plus 4x plus 4, so long as our denominator does not equal 0. Let's review some vocabulary. Let's start with, I'll do a 2x squared. So this number here in the front, that's our coefficient. We have our variable, and we have our exponent. This piece represents a term, and it's also a monomial. It's a polynomial of one term. And if we extend this and we add some other pieces, so 2x squared plus 6x plus 4, we now have we have a longer polynomial expression. In this case, it's a trinomial. So a polynomial is simply one or more terms connected by plus or minus operators. And each of our terms is comprised of a coefficient, a variable, and an exponent. Now, our rational, we bring this down here and we go x squared plus 3x plus 2 over x squared plus 4x plus 4. This is our denominator. This is our numerator. Think about the numerator is the thing being divided, the denominator is the thing doing the dividing. And this by itself, so this by itself is a rational expression. Now, if we set it equal to 0, or any other value, so we'll just say 0 to keep things simple. Now, this whole thing becomes a rational equation. And if we set it equal to some function name, in this case f of x, then this becomes a rational function. So if it's just the rational expression by itself, it's the two polynomials, rational expression. If we set it equal to 0, now we've got a rational equation that we can solve. We can find the values of x that make this true. If we set it equal to f of x, which is just another name for y when we're graphing, then this is a rational function that we can graph and we can get its attributes. So all of these are just different flavors of our rationals. Now, let's pause for station identification. So let's take a look at one of the most useful types of problems. And we're going to go distance equals rate times time, or d equals rt. That's a t. And this is known as the DIRT formula because it's so frequently used. So distance equals rate times time. And we do this all the time. We use this all the time. So say, for example, that we drive 55 miles an hour for 4 hours. How far did we go? We went 220 miles. So distance equals rate times time. And if we can work with these in a couple of different ways. If we were to set our rate as our constant, so we're going to say we're always going 55 miles an hour, then this becomes a constant of proportionality, and we have a direct variation. We have distance is equal to 55t. So however far we go varies directly by how much time, and the proportion is our 55 miles an hour. So that's just a direct variation. Now, suppose on the other hand, though, go back to this. We're going to go 220 equals RT. We set our distance as our constant. Now, we have 220 equals RT, and this is an inverse variation. Because the faster we go, the less time it's going to take. And so depending on which one we want to solve for, let's say we're solving for time based on our rate. So we divide both sides by R, and we get 220 over R equals T. Now, this is a rational expression. And this whole thing now becomes a rational equation. Now let's dig a little deeper into this. Explore a little further and see how this is working and what it's going to look like. Okay, for this example, we're going to need a car. But not any car. I need a roadster. I need a muscle car. So I got to throw my spoiler on there, put some good tires, got some window action, give it a fast color, got to have a supercharger and a blower on there, little window tint, and there's the car. So I've got my car. And let's say that we're going to go 500 miles. And we want to figure out our different rates and times. So again, we're going to have 500 equals rate times time, or 500 over rate equals time. So let's build us a table. So I'll start here. And let's say our rate's 50. Well, if we divide 500 by 50, then we get 10. And we're going to say this is miles per hour, and this is hours. Now, this is piddling along. Let's say we double this speed. Got to use the blower. We've got it, may as well use it. So let's say we go to 100 miles an hour. Now it's 500 divided by 100, and it's 5 hours. Now, suppose we have some nitrous on here, and we're able to crank this bad boy up to 200 miles an hour. 500 divided by 200, 2.5 hours. And let's say, for the sake of argument, that somehow we're able to get this we load it up on a jet transport, and we get this bad boy going 500 miles an hour. In this case, it's going to take 1 hour. Now let's suppose we load it up on a supersonic and we get it going 1,000 miles an hour. Now it's going to take half an hour. And in the other direction, let's go the other way. Let's say grandma's driving and we're doing 25 miles an hour. Well, 500 divided by 25 is going to be what? It's going to be 20. It's going to take us 20 hours. Grandma, you're killing me. Now, suppose we're having major engine problems and we're doing 10 miles an hour. Then it's going to take us 50 hours. And if somehow we're doing a mile an hour, now we're pushing the car, it's going to take us 500 hours. And if we were to keep going and say we do a 0.5, then it's going to take us 1,000 hours. So distance equals rate times time. When the distance is a constant, this becomes an inverse variation. And it becomes a rational equation. Now, let's do a quick sketch of this. I'm just going to sketch it. Now for a quick fast forward, we can see what's going on. As our speed increases, as rate increases, time decreases. But is our time ever going to get to zero? No, because there's no speed, there's no rate such that 500 divided by that rate equals 0. It's going to get closer and closer and closer. So we're going to say, but time never gets to 0. Time never gets to 0. Likewise, as our rate decreases, our time increases, but it never gets to infinity. Because our rate can never be 0. So this is a real-world application where we're looking at distance and rate, and or distance is set, and we're looking at our rate and time to see what changes. You'll also see these with work equals rate times time. Is another common use of the same concept. And we're going to be digging deeper into these as we go forward. But that's enough for today.